many drinks as you want. And we are taking photos today, and we're also live streaming. If you don't want to be on any of the photos, just let me know. We'll make sure you get cropped out of any of the photos you put on LinkedIn, Meetup, all that stuff. So just a shout out to all the volunteers. We've obviously got Josh and Samson over there operating the live stream for us. And just a few words from our sponsors. So first of all, so where we are right now, Avenue HQ, they, as the tagline says, they're connecting Liverpool's entrepreneurial community. So they have hot desks, spaces to work. Josh has just told me they're doing something really cool next month. Every Friday, I think, there's going to be an open hot desk day, which you can sign up for. We're going to send details about that on Eventbrite. If you are a remote worker, you want to come work in an office, just let us know. So we've got Alex here with Hyperloop. He's obviously works in recruitment. So if anyone is looking for staff or potentially looking for a new role, go and have a chat with Alex afterwards. And last but not least, we have got SNA. So they have a training program for junior engineers. So things like TDD, Solid, Radical Candor, they'll take your juniors and train them up for you. So take that workload off your senior engineers. So obviously, if you're interested in that, snaacademy.com. And last but not least, we have a giveaway today. So one lucky person is going to win a year-free JetBrains license, and you can spend that on whatever you want on JetBrains Ultimate, Rider. Rider's free now, actually, I think, but any of the JetBrains products. So all you need to do is scan that QR code. I think there's some on some of the seats. If not, Josh is going to pass one round. After the talk, we will pick one lucky winner. We're also, I lied, this is the last slide. Next month, in October, we're doing lightning talks. So if you want to practice speaking, you want to come along and give a 10-minute talk on anything you want, just let us know. Send a message on Meetup or LinkedIn, or actually grab me, Josh, or Samson anytime today. And I probably should know what the fire evacuation plan is, but it's that way. Yeah, that way down the stairs. There we go, we're all in. And now I'm going to hand over to Andy, who's going to talk about the nanoFramework. Cheers, Andy. There you go. And I'll remember to give you the microphone as well.
Yeah. There you go. Swaps over. Oh. Is that working all right? Tell me if the beard catches on it, because we don't want funny noises. Right. Okay. I'm going to switch over to the camera. So this is what we're here to talk about. So my name's Andy Clark. I currently work as a team lead for a dotNet team. I've been working for Mount Warehouse now for 5 years, leading various sizes of teams. I do mostly back-end stuff. Prior to that, I worked for a cruise and shipping company. So the last time I was in Liverpool, I was over the other side of the Mersey, wearing a boiler suit and hard shoes at some random dockyard, looking at cruise ships and things. So since then, yeah, it's moved on to nicer environment. Prior to that, I was in Imperial College doing electrical engineering. So I've got a bit of a background in electronics and a general interest. So it's a bit of a hobby topic combined with a work topic. So, hit the slides. Why did I think this was a good idea? So, as I said, we're a bit of a .NET shop. We do all of our back-end coding in .NET, bit of a React and other things on the front end. Mentioned a few people. We've got Java stuff going on in the stores. It's kind of outside my realm. So day-to-day, headless systems, no kind of interaction or anything. And we had a hackathon last Christmas where we kind of experiment with new technology, do projects. And I was given the task of coming up with a prize for this hackathon. So I was like, great, I'll get them some vouchers. And my boss said, no vouchers, got to get them something physical. So I was looking at different things. And one of the things I looked at was there's a board called a Meadow board, which is a hardware board that runs .NET. So I thought that was a good idea until I looked at the price and then went, I need something a bit cheaper than that. So I came up with these little yellow boards and they were kind of a fraction of the price of the Meadow ones. So I thought, great, I'll put .NET Framework on it. And that's how we got to where we are today. And of course, if you're working on kind of back-end systems all the time, there's no kind of interaction, you've got no sort of physicality about it. So I like the fact that literally I can pick this thing up and press buttons and tap on the screen and see lights flash and that. So I find that physicality kind of increases the engagement with the device, and the sort of the other side is because of all the constraints that you've got, the sort of limited memory, limited CPU, limited screen resolution, it makes you come up with more creative, inventive ideas. So by giving these to my team, my thought was that it can kind of push them out of their comfort zone and get them to try different things that they haven't tried before. But I didn't want to leave them completely in the lurch. So I needed to come up with basically a sort of a basic platform that they can play with. Okay. So nanoFramework, you get quite a lot for your money, actually. It's a combination of managed code in C#, and then some clever people have written some C#, C++ and C and assembler that actually sort of deals with the lower level stacks. So it can run on a multitude of different platforms. So at the top level, we've got the kind of stuff we're used to, application stuff, C#, application stuff. Next in, we've got what they call the base common library. Sorry, blanked for a minute there. So that's things that gives us access to the network, bit of some of the graphics stuff, general .NET things going on there. And you'll notice there's a little bit of a dotted line going on there. So some of that's in managed code and some of that's in C and assembly and the like. And that's going to come in very important later when we actually look to how we actually deploy this thing. CLR, you should be all familiar with it if you've been playing with .NET, so the Common Language Runtime. It's all the great stuff that makes C# very easy to use. And then coming down, we've got all the stuff that basically replaces the operating system. So the PAL is the platform abstraction layer. So that gives you access to just understanding how to read and write from the memory and some of the I/O and other bits and pieces. Then coming even lower down, there's the stuff that's specific to the device. So the hardware abstraction layer basically means that the people on all the layers above don't need to know what you're running the code on. So only the people down at the writing code and the bottom layers need to understand things like the features of the hardware in sort of intimate detail. So how do we get all that into there? And basically you follow the links and you follow this great long process that says, oh, you need to download these VMs. So download the VMs. You compile for your particular platform, you configure it all, and you get all the way to the very end, and you eventually compile some binary things that you can stick on the machine, and then they've got a nice little tool that you can put the image onto the machine. And when I got to that point, I realized I didn't need to do any of the stuff that came before, because there's some very handy pre-built, there we go, pre-built images. Well, this is where we find out whether the web's working or not. Pre-built images that you can use to stick on your devices. And you'll see that some of those are kind of specific to very specific hardware. So it was a Lily Go watch, and some of those are a bit more generic. So S3 is just a generic processor, C6 again. So some of them got additional RAM access, and some of them have got display access. We'll just scroll up. Let's try and work out how to scroll up. This was the one that was useful for me. Again, I picked the wrong one to start with, but I realized that there was a generic display one that worked quite nicely and had all the display libraries and everything I needed for the display board. So you then use this bit of software called nanoF to stick the images on the machine and see. Oh, it's moved. It was COM4 earlier. So you can find out what devices you've got connected. You can find out a bit about those devices. There we go, COM7. So it's going to tell us a bit about the chip, hopefully. No, that didn't work quite right. I picked the wrong command. You can't see it. There's a little sharing thing in the way of what I'm looking at. There we go. COM7. Oh, we missed one of the parameters off. There we go. Device. You click. Oh, and the hide. Yes, well spotted. There we go. So this tells us a bit about the chip. It's a ESP32. It's got Wi-Fi, Bluetooth, 2 cores, 240 megahertz, etc. It hasn't got any PS RAM. We'll see when we look at the other side of the board. And it's got a address because it is Wi-Fi enabled. So we can use nanoF. We can put a new set of firmware onto the device, and if you wanted to, you can play out and build your own. And it only took me like a couple of hours to actually build an image, which then I didn't need to use. It's all fairly straightforward to get you to the point where you've got a board. So that gets you all that lot. And then you have to write some C# code that actually does the application that you want to do. So my tool of choice is Visual Studio. You can also use VS Code, and to get it to work with nanoFramework, you have to install an extension. And apart from that, that's pretty much all you have to do. So let's just flip the board over and we'll. Yes, there is a little tool that tells you what the port number is, and you can pick that off the menus. So there's a other Windows Device Explorer. There we go. There's a little gadget, and it should hopefully pick up. There we go. COM7 Device Explorer. So yeah, the tools it installs a whole tool set for compiling the software and deploying it and generally interacting with the device. And there's a special kind of project file, which is a bit different from the usual project files. It allows it to use MS Build to build the binaries, and then basically pumps them over this serial port to the device, which we'll be doing shortly, hopefully. So what have we got in our software? Well, we've got system threading, system diagnostics, all kind of usual stuff. And then we've got a new one, device GPIO. So I mentioned earlier that GPIO stands for general purpose input out. And that's what we need to interact with the outside world. And then we've got some very specific stuff for the ESP32, which is what this board uses. And that allows it to understand a little bit more about that specific hardware. So these are all kind of coming in from NuGet, kind of stuff that you're hopefully familiar with if you're .NET developers, and all should just work basically. So let's talk through what we got on the code. Got main, which people are familiar with. We've created a new object called the GPIO controller, which is the object that talks to the hardware. We create some pins, and each of these pins on this particular device is connected to an LED. And let's have a quick look. So this bit here is a 3-color LED. It's got red, green, and blue, although I believe the red's broken at the moment. Other things that we've got, obviously, we've got USB-C on the right here. We've got a little audio amplifier down the bottom. There's an SD card, possibly. Oh, yep, top in the middle, yeah. It's bigger than I was expecting it to be. And we've got a bunch of yeah, so you can actually use it as a USB host as well, I believe.
This is very important when you're programming that board. So remember, you need to use the proper one when you're programming. You're loading the firmware, and when you load the program, you don't need to. You cannot use the same at the same time. One is you will use for programming, and another one for normal operation that you do it now.
So if I plugged a mouse into the other one, I couldn't put a mouse in here and program it at the same time. Yeah. The main processor is the thing on the left-hand side there, the ESP32 Vroom. So it's like a module. So if you lift the lid off that, you'll see there's a microprocessor and a bunch of other bits and pieces. We've got a couple of buttons down the bottom for rebooting and other bits and pieces. Can't remember exactly what connector it is. At the top, we've got 2 connectors, expansion connectors at the top, so you can get access to various GPIO pins on those. So as well as controlling those LEDs, you could control external devices, so you can maybe turn a relay on and off, or a motor driven from some kind of adapter board. Basically, you can't power a motor directly from it, but you could control it via a transistor or some kind of system like that. Okay, so there's our board. Let's go back to our code. So we've got red, green, and blue LEDs. Oh, we've got a debug line. So one of the advantages of using the Visual Studio over using the VS Code is that we get access to all the debug stuff, and we can actually put breakpoints in here and step through the code, which if you've ever used other microcontrollers, is like, wow, that's a bit of a game changer. Got to be a little bit careful there, because on microcontrollers, some things can be time sensitive. So if you breakpoint in the middle of something that's time sensitive, it ain't going to work. So you might need to sometimes just run stuff and then break and then run stuff. But you can do that. So we're just using, what are we doing here? So we're setting all the pins high. So the way the LEDs are connected is what's called a current sync. So basically what we do is we set the IO pins low to turn them on. So high means off, low means on. So it's reverse of what you might expect, but it's kind of actually quite common. So we're going to use the green LED, hopefully. We're setting the green LED low, and then we sleep, and then we turn it back off again, and then we sleep. And it's kind of, hopefully, fairly understandable code. So let's try and deploy this. Oh, let's just try it, start debugging, see how it works. Oh, yeah. Start debugging. Ugh. Oh, yep, it's working. And switch back to camera. Hopefully you can see. QED. green light flashing. So the blink sketch is kind of quite often the hello world of microcontroller sketches, because not all these boards have got access to do debug messages and stuff. So quite often things will just blink. So that's pretty much the simplest program you can do. So let's see if we can do something a little bit more challenging. Okay. So actually, I might pop back to slides first. Yeah, okay. I'm going to talk about libraries for a second. So as I mentioned, images is a bunch of pre-built images already there for you. The tool to put them on is this nanoF tool. And there's also a bunch of libraries that we can use using the kind of standard NuGet tools. However, the images and the libraries work together. So if you put on the wrong version of the image with the wrong version of the library, it won't work. So let's have a look at how that kind of manifests. Project, manage packages. So again, apologies to the non-developers in the house, but this should be fairly familiar for a lot of people. So this is the NuGet Explorer. We see we've got some very specific nanoFramework libraries. And if we have a look at the core library here, and I'm just going to get rid of that one for the moment. And we look at package details. There we go. Sorry, I can't make that one any bigger. What it says, this package requires a target with MS Core Lib 100.524 with a very specific checksum. So if you remember back to that diagram when we were looking at what the platform gives you, you've got some C# code and you've got some managed code. And basically what they're saying is they need to be as a pair. So you need to have the version of the C# code that matches the version of the assembly or C# code that's on the machine. A little bit fiddly the first time you come across this, but in general, it's not too bad. What you'll see is you can get the details of what's on the box by using a little device explorer thing, and it'll tell you here's all the various checksums and slightly bigger, and you should see, yeah, so the checksum is 1549 blah 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 56, and in the small writing on the right there we've got the same number, so the two are matching. So we've got some of the native assemblies, as they call them, so it's the C# assembly, and then we've got the managed code that is on top. Okay, now we go back to the slides. There's our blink. We took the various hardware. Right, it's going to get complicated. The serial peripheral interface. So the serial peripheral interface, or SPI, as I'm going to call it for the rest of the evening, is one of the ways that microcontrollers can talk to other things. It's basically similar to what we use USB for on the main kind of computing world. Just to confuse things, the ESP32 has 4 of these SPI buses, but you can only use 2 of them because it needs 2 of them to handle its internal memory and various other bits and pieces. You remember I said that there's this little metal box with a bunch of stuff in. Well, if you peel it off, that's what's going on. The other things in the box are needing 2 of those buses. And just to make things more confusing, the pins on the outside of the device can be remapped. So old school microcontrollers, basically, if pin 4 was reset, it was always reset. And if pin 5 was clock, it was always clock. Modern microcontrollers, pretty much you can go, I don't want to use pin 5, I'm going to use pin 12. and you just tell it and you swap the pins over, which is great if you've ever built a printed circuit board and got your pins modelled up, because you can just go, oh, well, I'll just change it in software, and you can swap them around, which is fun, but it makes it, can make it a bit confusing. The board itself has got 3 things connected to the SPI bus. It's got the screen, it's got the touch sensor on the screen, and it's got the SD card. So, how do we get 3 devices working on 2 buses? And that's where this set of pins works. How the set of pins works, basically. So we've got clock, which is kind of obvious. We've got peripheral out, peripheral in, controller out, also known as peripheral in, master out, which is kind of old school naming. So you'll see Pico and Mozzie and it was master and slave, and it's now peripheral and controller. So you'll see Mozzie and Mizzo as the other 2 namings of this, and you'll actually see it in the code later on. So basically is the data flow in one way, you've also got the data flow in the other way, and then this magic pin at the bottom, CES, is chip select. So what it allows us to do is go, well, actually, I'm going to be talking to the touchscreen now, and then later on, you'll swap it over and you'll have a second chip select pin, which allows us to talk to the second device. So we can actually have 5 SPI devices on each of the buses, so we can actually support 10 different things, and we've only got 3, so that's cool. Just to give you a heads up, I've only used 2 so far, so be interesting to see how we get the 3rd one working. I have seen demos in other languages that do seem to work, so hardware must support it. Just work out how we convert that into the nano world. Okay, so let's have a look at a different solution. We don't need that anymore. We don't need that anymore. Okay. Oh, when I came to work with this screen, what I realized was I needed a few more libraries, so that's fine. We've got the UI graphics driver libraries. And we obviously need to define what our various pins are. So we define our chip select and our, I think the pins are defined a bit further down. There's a reset pin there. It's actually for resetting the screen. And then there's a backlight pin. So I don't know if you are aware that these kind of little displays, the reason you can see them, let me just swap that around, is that there's a light behind the screen that shines through the liquid crystal display. So we need a backlight, otherwise the whole thing is blank. So that was the first gotcha, because the whole thing was blank when I first did it. So same as we had for Blink, we've got a GPI controller. So that allows us to control the backlight. And then for the screen itself, so some constants. We've got this SPI bus, and as I said, that's using the old school naming of master and slave instead of controller and peripheral. So the board comes with the data sheet, and the data sheet tells you what pins are connected to what. So you have to kind of work through the wiring to work out where everything is, or you could look at the code examples. But one of the things I've done in a later demo is I basically define these as constants that you can kind of use from a kind of shared library, just make things life a little bit easier. And as you can see, I've been using the classic approach of writing out debug messages to see how far I'm getting through the code. Because if you set the pins 13 and 12 the one way around, it will error because one of those pins can only take in, whereas the other one can take in and out. So I said you could remap the pins, but there are restrictions. And that's where you have to kind of read the data sheets again to work out which pins you can and can't. But the framework is really nice in this respect because it will tell us and it will error basically saying that you tried to write to a read-only pin. So once we've defined our pins, we can then define our SBI configuration and we can load our graphics driver with some default values. So the nice thing about the framework is it provides all the kind of basic functionality, and then you have to write the specific code that makes the screen turn on. So again, if you look at the data sheet, basically there's a whole raft of configuration that basically says what's the screen width, which way around does the data get presented, so is it big small or is it small big when you're sending serial data to it, and all that's again in the data sheet, and conveniently somebody's written a library for us that did everything that we needed, except when I first put it on, my text was backwards, so it was an exact mirror image of the text that it should have been. So I did actually need to customize the driver a little bit to make that work. So you can do sort of landscape portrait upside down, but if you think about it, there's actually 8 orientations if you include the mirrors as well as the rotations. So it's one thing I need to kind of feed back to the dotNet world, the framework world, is that actually they need to support 8 orientations, not 4 orientations. Anyway, we set that up, we set up a screen, we initialize our display. This is where it will error if you try to, oh, actually, no, that's not one. That initialize will be where it errors if you get the pins wrong. And likewise on the backlight, if we try to do that to a read-only pin, it will tell us that we've got the wrong pin. And then blank screen is a function I've written. Color comes with the library. And display text is something I've provided. And bitmap. So, some bitmaps. Something that is pretty straightforward in desktop applications. You just write text to the screen, you write bitmaps to the screen. It's a little bit more complicated in the nanoFramework world. And the reason it is that the board doesn't come with any fonts, like an operating system would. You'd have a bunch of fonts available. So what you have to do is you have to define those fonts, and you have to load them in as resources. So I don't know if anybody remembers the sort of old school Windows program where we had resources and bitmaps and fonts and everything had to be included in as additional components. But basically what you need is you take a tool called TinyFont, and it will convert your fonts into fonts that can fit on a microcontroller. And then we'll see when we look at the display text function that actually ends up really quite simple. One of the nice things about the TinyFont is if you only want to put 3 letters in, because you're not actually displaying the whole alphabet, you can just pick those 3 letters that you're displaying. And that means you get a load more memory for other things, which, for example, a bitmap. Okay, so let's have a look at these functions. So display text, pretty straightforward. We get a font and we get a font color. We'll come back to that in a second. And then we just display control write text is just a function that's provided by the framework. So nice and straightforward. Come back to the color for a second. Actually, I might need to load this up first. Let me just deploy this. Yeah, there's my solution window gone. Just going to deploy this so we can have a look at the screen. So if it works, yep, it's deploying. It's very small numbers incrementing faster at the bottom of the screen. And let's have a look at the camera. No, that's not worked. Let's reboot the thing. Reboot. There we go. So you can just about see the little tiny pixels on the screen here. If we had a microscope, we could zoom in a bit further and you would see that each of those pixels is actually made from 3 tiny little pixels, one red, one green, and one blue. Except they're not. It's one blue, one green, and one red. So again, something that you don't necessarily need to worry about on desktop apps. You need to swap your colors around. So we do have some bits of code that will convert RGB to BRG in this case. And that's just a rearrangement of bits in a byte. Yeah, so, and then display is fairly straightforward. And we scroll down again. Oh, no, program, please, program. We'll scroll down. We'll have I think we've got clear screen somewhere. Yeah, we have a blank screen. So blank screen, we've got a clear method, but I wanted to clear it in a different color. So basically I write out the whole screen. In this case, I would write it out in white. So that blank screen is black, so I wanted a white background. So again, it's fairly straightforward code. We've got a loop. We've got an array of 100 characters. And then what do we do? Ah, yes, we're writing it out in little chunks. So the reason we're writing it out in little chunks is that we haven't actually got enough memory to hold the whole of the array in memory. So we'll write it out in smaller bits. So it's writing out actually a 10 by 10 blob repeatedly across the screen to get the thing displayed. So as I said at the beginning, the kind of restrictions means you have to be a bit more creative in how you write the software. But I think hopefully at the end of the day, it's fairly straightforward what it's doing. It took me a while to remember what I'd done. So that's blanking the screen, and displaying bitmaps is pretty much the same. So I created a blit bitmap function. So basically we take in the source bitmap and then we write that out in little chunks onto the screen. So how do we get the bitmap into the software? So again, there's another bit of utility software you can use that does that, and it will convert your logo. In this case, it's the dotNet nanoFramework logo, and it converts the logo into a whole range of numbers. For those slightly older in the audience, we remember typing these kind of things in from magazines. So luckily there's software and we can just copy and paste it nowadays. So our bitmap comes in as a file, our font comes in as a resource. You could probably do it as a resource as well. And then, yeah, we just chuck it on the screen. So that was the screen. So that's one of the SPI buses. The other side of things was the touch sensor. So let's see what we did for touchscreen. So we've pretty much got all the same kind of stuff that we had for the main screen, but to get the touch sensor working, we want to be able to click on the screen, maybe press buttons and generally interact with the device. And it's got what's known as a resistive touch screen, so it's a little bit temperamental, and you do have to kind of really kind of push it, but comes with a little stylus that you can sort of tap on it and it does kind of work. So for this one, as I mentioned, I created a little library with all the pins for various bits and pieces. So we've got all the display pins, we've got all the sensor screen, touch sensor pins, and there's a few other bits and pieces in there as well. So again, similar code to before. We've got GPI controllers for dealing with things like backlights. But we've got some new stuff as well. Let's have a look at what we've got that's new. Here we go. So for the touch sensor, we need to configure which pins are used by the SPI bus. And a little bit of annoyance with the way that the nanoFramework works is that we've got a completely different SPI configuration thing for non-display devices than we do have for display devices. And we also have just here the bus that we're using. So I mentioned that there's 4 SPI buses. The 2 internal ones are kind of hidden away. So we've got bus 1, which I'm using for the screen, and then we've got bus 2, which I'm using for the touchpad. Okay. And there was no driver at all for the touchpad. So I had to come up with a way of doing that. So let's have a quick flick back to the slides. So there's our display. The touch screens are surprisingly complicated. But basically, we've got 2 things going on. We've got a special pin that tells you when things are happening called an interrupt pin. And then we've got an SPI bus that basically you can use to interrogate the device and work out which bit of the screen is being touched at any one point. Getting messages to and from the touch screen was a little bit challenging. All that was hidden away in the display drivers. Didn't have to worry about that at all. But for this, we're actually kind of in a slightly lower level, and we had to work out how to talk to this thing. Quite clever. It uses what's called a successive approximation controller. Converter, sorry. So you'll see down the bottom here, we've got bits 11, 10, 9, etc. coming in. So basically what it does is when you tap on the screen, it looks basically at the distance from that tapping point to one edge of the screen and the distance from the tapping point to the other end of the screen, and basically creates an analog number that ranges from one to the other. So what we do is we send a message that says, I'm interested in the resistive thing that goes that way, or I'm interested in the resistive thing that goes the other way. So that's the message you send it, and then you keep pulsing the clock, and it starts at the high level, and it goes, oh, okay, it's about there, and then it goes, well, actually, you're basically dividing by 2 each time, so you get slightly more information as it clocks it out. And you'll notice here that they're actually sending another message to it before it's finished. And I tried to do this, and it's a lot harder than you might expect it would be. So the library that wraps the SPI bus basically allows you to you can send a message, you can receive a message, and you can send and receive at the same time, or a full duplex as it's called. The problem is that when you get to the end of that, it basically resets, and when it resets, the touchscreen controller goes, okay, I'll reset then. So if I try to send 2 messages and then stop, it would reset the device and the second message basically is lost. So what I'm doing in the version of the library I've got is basically I'm just shifting this across to here. So I've got 3 bytes, and I'll send 1 byte with all the control information and then 2 blanks. And those 2 blanks is when it's reading back the data here. And then those control bits for reading X get on the next 3, and then the Z, which is the pressure, is on the next tree. I did realize after I'd written this that it was actually possible to get it to work with this overlapped mechanism, but you just have to read the whole thing in one go. So you'd have to go, give me X, okay, I'm reading X, give me Y, I'm reading Y, give me Z, and I'm reading Z, and then finish, at which point the thing resets. But if you try to break it into 3 distinct chunks, it will reset halfway, and as I said, you lose basically the messages in the middle. So that took me a while to work that out, but once that was sorted, it was communicating fine. So what else have we got? Yeah, so let's have a look at how interrupts work in the software. Okay, so we've got a GPIO controller here on line 78. And we open the pin, and previously we've been opening it as an output for turning the lights on and off. We're now opening it as an input with a pull-up. And basically, the way the interrupt works is basically it's either not connected at all or it's connected to ground. So what that means is you, as the information that's coming in that binary, it's like, oh, I really don't know what it is. And then it's like, oh, it's definitely on, or it's definitely off, I suppose, if it's pulled down. So the pull-up basically puts a resistor in place that says when there's nothing connected, bring it high, pull it up. So when there's nothing connected, it's high. And then when the screen is touched, it pulls it low, and we get a signal. So we get rid of the Solution Explorer because it's quite wide at this point. Oh, that didn't really work, did it? I love whoever invented this method. Register callback for pin value changed event. Tells you exactly what it's going to do. So basically, we are wiring up this bit of code here to the event on that pin there. The device config is the pin number, and on the type of falling. So as you mentioned, we're pulling up the signal to high. When the controller has an event, it pulls it low, so it falls. So it's high to low, a falling event, and it causes a bit of code. Now, those that use low-level microcontroller stuff, where's the control function? There we go. Those that use fairly low-level microcontrollers will know that when you've got an interrupt, it is literally that. Everything stops until that interrupt routine is completed. Now, apparently in the nanoFramework, there's a few nice wrappers and stuff, so we don't actually need to worry so much. But I've kind of applied that same principle here, and basically my callback function is doing one very, very small thing, which is setting that touch detected to true. So I've got a Boolean flag. It's normally low, and in fact it gets set low, as you see a few lines above. And then when the screen's touched, the flag goes high, and we can pick that up in the other bit of the code. So there we go. If it's touched, we ask the sensor to get the point, and that does all that complicated SPI stuff. Comes back with a point, which is X, Y, and Z. And then we're doing some various checks to see if it was touched or not, and it's going to write on the debug whether it's blue, red, or another color. So let's see if we can get this uploaded and sent. Build, deploy. Is it going to go? Oh, yep, it's working. And I'll just reboot it. There we go. I don't know if you actually spotted how long that takes to do that. Actually, just unplug it. So you can see it's off. And basically, by the time I've plugged it in, it'll have actually drawn the screen. There you go. This is another thing I like about these kind of physical devices, which is like, if I was building a computer from scratch, I'd still be making my coffee at this point. Whereas obviously the things like the microcontroller are a lot faster. Same gotcha I had with my text. The thing was mirrored. So where I thought was 0 was 1, etc. But eventually worked it out. Hopefully you can see on the screen, there's a blue, green. The red's a bit on the far left of the screen is red, and on the far right is yellow. They're not coming out. It's not too much contrast on those. And if we look in our output window here, hopefully I don't need to have the stylus. Maybe I need the stylus. Might need the stylus. We just grab the stylus. I said the touch screen is a little bit sensitive if you're used to a kind of mobile phone. You don't have to use a stylus with a mobile phone anymore. There's always one demo that doesn't work. This one is today's touchscreen. I'm not. Thank you very much. I'm not debugging. There's where we're going wrong. Well spotted. There's no device selected. Let's try that again. I don't think it is the port that's wrong. I think it's that it's not deployed it as a debug. Yeah, man. Start debugging.
You need to connect into different USB ports, and they
Sorry?
they use different COM port.
I'm fairly certain it's not the COM port, but let's have a look and check. View, other windows, Device Explorer. Oh, it's close. It's forgotten to find it for some reason. Yeah, it's lost it. Can't find it for some reason. We can do a hard reset by holding down the buttons and putting the power back in. Hopefully that, there we go. Hopefully that's gonna turn it off. Yeah. Should be to rescan.
All 7 ports blocked right now. We need to connect into different USB. 6 ports after that they choose different COM port, and you will get chance to connect your device.
No, it's
because you disconnect the device when the application uses the
Yeah, but it automatically detects the COM port on the device window.
No,
It's
never happened.
I think what the problem is because it's busy doing its bit of software, it's not available for for debugging. So as I said, let's I know what you're saying about it being a different COM port, but it would come up and it would say it was a different COM port. Yeah. We don't need to restart the computer, but we do need to. We can check the Windows Device Manager, yeah.
Standard users.
Where are we? Oh, there we go. Yeah, unknown device. It's not recognizing itself at the moment. Sorry? What, the other end? We could try that. Hey, there we go. Hey, brilliant. Okay, so we're back online again. And now we can do the debugging as suggested. It's doing the deployment. There you go, figure that one end of the cable is more important than the other end of the cable. Right. We're running, it's initialized. Go on, play with me. Red. Green. Blue. Come on, yellow. You know you want to. Yellow. Yeah, so the USB driver needed resetting, didn't it? Yeah. But you can also get the case where the device is too busy doing anything to talk to the debugger. So that's what I was trying to do the first couple of times. But thank you very much for helping me reset that port. And okay, so there's our touchscreen. What next? So I mentioned there's a whole bunch of other things on the board. There's an audio output. It is, sorry? There is I2C, yeah, on one of the connectors, yeah. So you could attach other types of sensors. So you could attach like a compass or a temperature sensor or a humidity sensor, something like that. There's also, I've not mentioned it here, but there's analog input. So you can have like a slider or a turning knob to pick up that kind of stuff. There's obviously the SD card. The Wi-Fi I've not played with at all. And I probably will do some more stuff with the graphics. Probably get that touch sensor working a little bit better than it's working at the moment. But yeah, that's my plans for what is next. That's me. Workshop shared in most places. I'm on some of the old school social medias as well. You'll normally just get the automated messages on those. And here's some of the various other projects I've worked on over the years. This one here is what won me a trip to New York. It's a weather house that talked to the internet. And I'd probably use something like that nowadays to do that rather than quite a lot of electronics. But that was a competition where basically they provided the electronics and you had to basically do your best with them. And I wrote a basically a kid's fairy tale story wrapped around electronics. So Hansel and Gretel, actually no, it was Boris and Matilda, I think actually, lived in a forest and they were interested in the weather. And the big bad wolf used to come along occasionally and spoil their day by doing things like removing the power or removing the internet connectivity. And the story looked at things like, well, how do we do battery backup? How do we do internet security? And then how do we talk to the various sensors that do the weather? So basically there was, we talked to the weather service and then the backup was the local sensors. Yeah. And we're done. Oh. So that's my bit done. These guys have got bits to do, haven't they? There's a prize.
Well, before we do the poll.
Yep. Oh yeah. Oh.
Is there a advantage to use net instead to use C, normal C?